Welcome. In this session in linear data analysis, we'll explore the application of kernel PCA to a simple data set. What we'll do is we'll use Ronald Fisher's IRIS dataset. These were data that were collected in 1935 and 1936 on the Gaspé Peninsula of Canada. They were of the iris flower, and there were 150 observations. There were 4 variables. These were the length and width of the petals and the length and width of the sepals. Previously, what we've done is we've divided out the petal data or the sepal data. Now we'll leave this as a 4-dimensional data set. We'll label the beachhead type, which is Iris setosa, as our +1 label, and the other 2 species will gather into a single -1 label. We'll perform conventional PCA. That means we'll find the zero mean data and we'll reduce this down to 2 dimensions, and then we'll use k-means clustering to divide the data set. Then we'll try kernel PCA. For kernel PCA, we'll use a Gaussian kernel, and we'll use as our hyperparameter sigma squared the number of observations that we have. We'll also use k-means clustering to divide the data. So let's take a look at what conventional PCA does. So what conventional PCA would do is it would project the 4-dimensional data down to these 2-dimensional data. And this has a shape that we haven't seen in other sessions, but this is the group of the beachhead type iris, and then this is the collection of the other 2 species gathered together. If we perform k-means clustering on this data, this is what we see, is that the beachhead type, the Iris setosa, has been correctly clustered using k-means, and there are 2 anomalous ones, and we've come across these anomalies repeatedly in linear data analysis. Now, let's compute the gram matrix, so that'll be a 150 by 150 matrix, and then one of the first things we like to do in linear data analysis is a discrete plot. So what we do is we plot the singular values or the eigenvalues, it doesn't matter, and we'll use some normalization method or other. And what we see from this discrete plot is that the first component explains approximately 75% of the data. If we add one more component, we've explained a lot of the data. And so what this is suggesting is that 2 dimensions will suffice. So now we'll take kernel PCA and we go through the scores and we get 150 kernel scores. So these now have little hats on them. So this is the first score, this is the second score, and what we see is that the beachhead type irises are in this cluster, and then, that they have this label, and then the other 2 species have this label. Now we'll take this this result of kernel PCA and we'll apply k-means clustering to it, and what we find is that the clustering performs very well on the iris data. So, what have we learned in this lecture? Well, we're now able to compute a gram matrix from given data. We can center that gram matrix for the purpose of kernel PCA using a centering matrix. We can compute scores using kernel PCA, and we can now assess the results using simple data.